SwayamPrabha. Digital India. Educated India.
So our second speaker is Ji In-soo from National Tsinghua University, Taiwan. So are you presenting online or do you want to play the video?
Okay. Good afternoon, everyone. My name is Ji In-soo, and I'm a PhD student from National Tsinghua University. I'm delighted to be here today to talk to you about a reinforcement learning approach for stochastic cutting stack problem. This presentation will cover 5 sessions: introduction, the problem statement, our proposed method, the result, and conclusion. First part is the introduction. In a production scheduling for chemical industries, such as copper foil manufacturing, the inventory level directly affects the production cost. The stochastic cutting stack problem, SCSP, can be considered as a complex inventory level in scheduling problem due to represents of random event factors. With traditional deterministic mathematical methods, such as integer programming, the computation time of the solution grows exponentially with the complexity of the process. Reinforcement learning, RLO, is a novel method to immediately provide the best scheduling solution. However, RLO is doubtful if it deals with process constraints. Petamburan-Neto and co-writers provided a model free of policy approximate policy iteration algorithm to show the RLO scheduling performance and ensure that action doesn't violate the constraints. Yet, the exhaustive random iteration and the excessive mathematizations led to huge training time, making industrial applicability low. The purpose of the study was to adopt advantage actor critic A2C for continuous action space to solve a SCSP for more reproducible and easier implementations in industry. Also, we propose a 2-stage discount factor algorithm for training a model that could make a well trade-off between 2 goals, avoiding violated constraints and providing the lowest cost. Next session is the problem statement. We use the SCSP example adopting Petamburan-Neto and co-writers research. There are 30 pieces of 1,500 centimeters raw material, known 15 cutting patterns, to be cut into 7 different items with random demand, and minimize the trim loss, bad order, and order inventory. The range of 7 items was shown as Table 1. The composition and the trim loss of each pattern were shown as Table 2. Take pattern 1 as an example. It is composed of 10 item 1 and 1 item 4, with a trim loss of 36 centimeters. To obtain a random demand of each item, the total demand, which is a uniform distribution ranging from 40 to 50, was first sampled. And the demands of 7 items are a multinomial distribution based on total demand and probability vector P. Next, let's focus on the method we employ. First, reinforcement learning RLO is a decision-making method involves an agent to interact with the environment, shown as Figure 1. The agent observes a state from the environment, then determines an action to take, and the environment returns next state and reward. The goal of the agent is to maximize the reward. Therefore, RLO develops a policy for choosing action depending on the state. RLO can be divided into value-based and policy-based. The main difference is whether an explicit policy be trained. In the value-based learning, well, there is no explicit policy be trained. Policy selects the actions by the value function instead. In the policy-based, an explicit policy is built to determine the actions directly. RLO can also be divided into on-policy and off-policy. The main difference is whether the policy which is improved, called as target policy, is same as the policy that is used to select actions, called as behavior policy. In on-policy learning, the target policy and the behavior policy are the same one. Therefore, only the current data can be used for training. In off-policy learning, the target policy and the behavior policy might be different. Thus, the historic data can also be used for training. We adopt a reinforcement learning algorithm called Advantage Actor Critic A2C for our SCSP example. A2C is an on-policy method in RLO, which can only be trained by current data. A2C combines value-based and policy-based learning, which is composed of two neural networks, actor and critic. Actor is the policy which determines the action. Actor is trained by minimizing the actor loss that increase the probability of action with a large advantage value. Actor loss is formulated as shown on the right. It should be noted that the advantage value is calculated by reward and state value. Therefore, there has only one critic network needs to be trained. Critic is updated by temporal difference, indicating that the critic loss is formulated as shown on the right. Gamma is the discount factor that between 0 to 1. The closer to 1 means the more time steps of future rewards to consider. Gamma is a critical hyperparameter which we paid attention in this research. Commonly, entropy loss will be used during training of the actor and the critic. Entropy loss allows the actor to maintain the ability to explore at the beginning of training, avoiding falling into local optima. The actor network of A2C output the probability of discrete actions traditionally, but A2C is also a potential method for dealing with continuous action space. For continuous action space, actor network outputs two scalars. Each have size same as the number of actions instead of outputting the probability of actions. One of the scalars represents the mean value of the Gaussian distribution, and the other one represents the variance. While addressing the continuous action space, the actor loss and the entropy loss are calculated by the mean value and the variance, which are different from the discrete case. The critic loss is independent of actions. Thus, the critic loss is same as the discrete one. The structure of critic and actor neural network was shown as figure 2. The proposed process diagram was shown as figure 3. The proposed framework is composed of two parallel parts. The first part is the interaction for data collection, which is the solid line in figure 3. At the beginning of an episode, the initial state was sampled and observed by actor. Actor then output a mean value and variance for sampling the actions from Gaussian distribution. After executing the action, the environment returns the next state reward and whether the episode was done. If the episode was done, the next episode started and the initial state was sampled. If not, the next state was observed by actor to take the next action. The second part is the training of the critic and actor, which is the green dashed line in figure 3. After each 32 steps of interaction between the actors, the total loss, which is composed of critic loss, policy loss, and entropy loss, was calculated and was used to update both the actor and the critic network. It should be noted that if the episode ended at time state t, then the state value of time step t plus 1 would be 0. Furthermore, we propose a two-stage discount factor shown in an orange square. After once the mean gain steps over previous 100 training episodes larger than 200, the discount factor will be adjusted to 0.1. Before that, the discount factor is 0.9. Next, I'm going to explain the environment system. The state of the system is the inventory of each item. The initial state will be sampled from a uniform distribution ranging from 0 to 35. The action is the number of each pattern to use. The cost function is formulated as list function, which is composed of string loss cost, inventory cost, and backorder cost. The reward is then calculated by dividing 500 by the cost. The action is restricted by two constraints. The first is that the inventory of each item cannot exceed the maximum inventory. The second constraint is that the total number of patterns to use cannot exceed the amount of raw material. If the action violates the constraints, the episode ends. If not, the state updates by the below function. While calculating the critic loss, which is based on temporal difference, the discount factor is critical for determining how far the future rewards to consider. The closer to 0 means the less time states of future rewards to consider. Thus, the actor will try to do the best just for right now. There are two goals to achieve for our agent: avoiding violating the constraint and providing the lowest cost. According to different goals, we set an adaptive discount factor with two states shown as below. When the constraints are satisfied for more time steps, the higher the accumulated rewards. Therefore, we set a higher discount factor first, which means long time steps are considered, aiming to train the model to meet the constraints continuously. As the average of total time steps for continuous actions that satisfy the constraints larger than the lower bound ones, we set for 200. The discount factor adjusted to 0.1. At this stage, the target of the agent was to take an action which could lead to the lowest cost. Next, let's check the result. We trained 3 models, including our proposed two-stage discount factor with value 0.9, and discount factor with value 0.1. Each model was trained with a fixed training state, not a fixed training episode. The total states of each episode might be quite different, according to the model's ability to deal with the constraints. Therefore, the total training episodes of each model might be different. Figure 4 and Figure 5 show the training curve by mean-gain states, which were averaged over previous 100 episodes of 3 models. Figure 6 and Figure 7 show the training curve by mean cost, which were also averaged over previous 100 episodes of 3 models. The training of the model with a discount factor equal to 0.1 was obviously slower than the other 2 models, resulting in a much larger training episodes, making it difficult to show on the figure together with others. The higher the mean-gain states, the better the ability for agent to continuously provide actions that satisfy the constraints. Figure 4 and Figure 5 both show the gradual increase in the mean-gain states, indicate that the agent learned to take the action satisfy the constraints. Two-stage discount factor algorithm trained the fat test with mean-gain states greater than 7,000 after training. The algorithm with discount factor equal to 0.9 trained slightly slower with mean-gain states greater than 200 after training. An algorithm with discount factor equal to 0.1 trained the slowest, with a mean-gain state was about 15 only after training. For a model of discount factor with value 0.9, although the agent learned to take the action satisfy the constraints, Figure 6 shows that the mean cost didn't decrease, indicating that the model cannot deal with the constraints also with a low cost. For the model of discount factor with value 0.1, Figure 7 shows the gradual decrease in the mean cost, indicating that the model leaks when dealing the constraints, but has potential to reduce the cost. The surprising result shows that the two-stage discount factor reached a sufficiently low cost of around 500 with a high mean-gain state. Furthermore, the results show that adjusting the value of discount factor according to the training purpose in different training stages, can accelerate the speed of training, and also achieve both the goals of continuous propagation, the meta constraints, and the low cost. We evaluated the performance of models by two methods. First of all, we tested two-stage discount factor model for 1,000 time states and average over 10,000 simulations, shown as figure 8. We got a result that the average cost was around 520. It should be noted that the other two models couldn't continuously propagation for 1,000 time states. Thus, this test was only for two-stage discount factor algorithm. Secondly, we tested three models for 100 episodes after training. We got the results show that our proposed agent had the highest mean gain state and the lowest cost. Discount factor with value 0.1 had the smallest mean gain state, and discount factor with value 0.9 had the largest mean cost. Our A2C agent can surprisingly continuously propagation that met the constraints for over 10,000 iterations with a mean cost equal to 462.75. For our booth, we've covered that our proposed method solve SCSP and obtain a low-cost solution with several advantages. First one is the ability to deal with constraints. The result of mean gain states show the excellent ability of our proposed method to deal with the constraint without excessive random iterations. Second one is a reproducible, practical, and short training time. Our method has a small number of hyperparameters to be tuned, which is reproducible, practical, and easy to train. Next one is intelligible. Our proposed method is common and simple to understand. Furthermore, the two-stage discount factor algorithm could train a model faster and show nice trade-off between two goals, avoiding violent constraint and providing the lowest cost. Finally, these are the references. This is the end of my presentation. Thank you all for your attention.
Okay. Thanks for finishing time. We have 2 or 3 minutes for Q&A. So, does anyone have questions? Yeah, go ahead.
Thank you for your presentations. In this study, I think continuous actions is driven from the mean and variance, which is given by the actor. Sorry, basically, even though we regulate the variance, a range of the acting by minimizing the variance, but actually it is driven from the Gaussian. So maybe the actor provides some. My question is that anyway the action is driven from the Gaussian. So how could you regulate the range of the action?
Could you repeat your question again with some of the speakers?
My question is that the action is driven from the normal distributions. So maybe the action range is outranged from your system or something. So is there any some methods or the criteria to regulate the action which is sampling from the Gaussian?
Excuse me? You mean that the range of my actions? Sorry, can you repeat the question again?
I think that the system has some range about the actions, but in actor critic reinforcement learning, the action is sampled from the normal distribution. So is there any way or some criteria to regulate the range of the actions which is given by the actor?
We didn't say the range by the network or other method. We just use the constraints that if the action over the range, the episode will be end, and the rewards will the accumulated rewards will be quite small. And we try to learn the reinforcement learning agent to learn the action won't over the range.
Do you hear a voice?
I think I need to skip that.
Yeah, because we have some technical difficulties with microphones. So I will send you the question directly to you and continue the discussion. So unfortunately, we're going to stop the second presentation here and move to our next one. Let's thank our speaker again.